Now, something else that you might have to learn is the theory of the Big Bang theory. So the Big Bang theory basically states that there was an explosion, or at least that's how most people know it. It's not an explosion; it's a rapid expansion, from which we now have everything in the universe. And the universe is still expanding and cooling down, and we start counting time from the beginning of the Big Bang. So a rapid process of expansion. Now, obviously, that meant that there are quarks and that meant that there were different very small elementary particles at the very beginning, and then those elementary particles gave rise to more complex particles. Then you have black matter, and then you have the formation of more sophisticated chemical structures that led to the formation of planets and other celestial bodies. What happens is that these elements actually decay, and we measure decay through half-life. Half-life is basically the amount of time that it takes for half of a substance to decay, and then the other half to decay, and then the other half to decay. When decay occurs, radiation is emitted, and radiation can be in the form of alpha, beta, or gamma radiation. Alpha is the simplest and easiest radiation to stop. It can be stopped by a sheet of paper. Beta particles are the more complex ones to stop. They can be stopped by an aluminum sheet. And gamma rays are really difficult to stop. You need lead, steel, and concrete. Alpha particles, they are the same as a helium nucleus. A beta particle is similar to an electron. And gamma rays refers to electromagnetic radiation. I'm going to come back to that. But basically, what we're going to learn, or what you will learn more eventually, is that elementary particles are not just protons, neutrons, and electrons. There is also something that we call quarks and antiquarks. So antiquarks are the antimatter of quarks. And when quarks and antiquarks collide, they will lead to radiation because they will annihilate one another. They are basically the opposite of each other. Quarks and antiquarks are basically the opposite of each other. Quarks and antiquarks are like two matters which are the opposite, right? Now, when we categorize quarks, we say that baryons and mesons are under the umbrella of hadrons. If you are now panicking, given the amount of terminology that you need to know, I would caution you guys not to stress too much. Ask any questions using the chat box, but you don't need to stress. It's not that... It is important, don't get me wrong. It is very important, but there are more important things to remember. For example, Einstein's mass-energy equivalence, where Einstein stated this formula, E equal to mc squared, where m is the mass in kilograms and c is the speed of light, which is 3 times 10 to the power of 8 squared. It's essentially it revealed that there is an inherited energy associated with mass. So when we look at fission and fusion reactions, where fission is the case where two particles collide with one another, fusion is the case where two particles collide with one another to form a bigger particle, and that's fusion. And then fission is when a bigger particle breaks down into two smaller particles. If you were to measure the mass of the reactants and the products, you would see that they are not equal. The mass of the products is actually slightly less than the mass of the reactants. And The reason for that is because some of that mass has been annihilated and it has been released in the form of energy. This energy can be electromagnetic radiation. And that is where Einstein's E equals to mc squared became very useful, because it shows that if there is a difference in mass between the reactants and the products, we can actually then calculate how much radiation or how much energy has been emitted, which is really cool. For those of you who don't know, there is a law in chemistry stating that the mass of the reactants and products should be equal to one another, because if mass and energy are one and the same, or they can be converted to be one and the same, we know that there is a law, which is the law of conservation of energy, which states that the total energy of a system cannot be created nor destroyed. This means that mass in a reaction cannot be created nor destroyed out of nothing, right? So if something breaks down into smaller parts, it means that if you add up all those parts together, you'll get the bigger molecule that you initially had. If that doesn't happen, then it means energy has been released, it has been radiated somewhere. But it doesn't mean that that energy that was associated in the bonds forming that particle disappeared into nothing. Bonding energy curve, fusion and fission, electromagnetic radiation. So when it comes to electromagnetic radiation, because as I said, energy is going to be emitted in the form of radiation, when it comes to electromagnetic radiation, it's actually a propagating electric and magnetic field, which are perpendicular to one another. Usually we conduct, in Australia, these experiments are conducted in something called the synchrotron, which is a particle accelerator. And this slide here, I forgot about this one. This slide here is only there to state that the Bohr's model of the atom was that there are protons and neutrons in the nucleus, and the electrons flow orbit around the center, the nucleus.